All right, so Newton's third law questions, they're also known as connected masses or connected objects, okay? And so what they're involving are two objects that are connected together by a rope, by a string, by a cable, by a hitch, okay? And Newton's third law, if you remember the three laws, first one, an object in motion stays in motion, an object at rest stays at rest unless acted upon by an unbalanced force. Second one, if acted upon by an unbalanced force, that force will accelerate the object in the direction of the motion. That's where we get F equals ma. And the third one is that for every action, there must be an equal and opposite reaction. If one object exerts a force on another object, the second object must exert an equal and opposite force back. So we have the horse here exerting a force on the cart. And so the cart is exerting an equal and opposite force back on the horse. These two have to be equal. Some people will say, but wait, if they're equal, then this horse and cart system won't move at all. What's going to determine if they move is like the forces acting on the cart or the forces acting on the horse. These two forces are acting on two different objects, so they can't cancel each other out because they're on two different objects. So if we look at the cart, the forces acting on the cart, and I'm just going to draw it as a box now, is the force that the horse is pulling forward with, and then whatever friction might be acting backward. If the horse can generate enough force to pull with a bigger force than friction, then the horse is going to be able to move the cart. On the horse, and again, it's going to be a box. I can only draw so many back ends of horses. The cart is pulling back on the horse. And the horse is also pushing down on the ground, so the ground would be pushing forward. So this is the force that the horse is generating with his leg muscles in the ground. If the horse can generate enough force between it and the ground, meaning like if it's not on ice or like something mud that it's sinking through, then the horse will be able to overcome the backward pull on the cart and the horse will accelerate. Now, when the two of them are connected together as they are, whatever the horse accelerates with, the cart will also accelerate with. And so you can look at the horse, you can look at the cart, but you can also look at the whole system, the horse and cart together. And we could draw it as like one box and do cart and horse. So forward on the cart and horse is the force that the horse is generating with the ground, and backward will be the friction that's opposing it. If we want to find the acceleration, we probably would want to do it on the system because lots of times we can figure out the friction on the ground. We might be given what the horse is generating, but this force, this horse on the cart, cart on the horse, they are equal and opposite to each other because of Newton's third law. They are often called like the tension in the string or the connector. What has to be true is whatever the acceleration of the system is, that must also be the acceleration of the horse and the acceleration of the cart. Grab someone's arm and run out of the room, accelerate as fast as you can. They either need to go with you with the same acceleration or lose their arm. So if the horse and cart are staying together, whatever one accelerates with, the other accelerates with. Okay? So as we do these questions, we'll look at the whole system, and when we do, the tension in the connector doesn't come into play because the tension in the connector doesn't actually change the motion of the system. The motion of the system is determined by what are called the external forces. Forces that are acting on the system, on the objects of the system from the outside, like friction and like the force that the ground is pushing with. The tension here, it's known as an internal force. It does not change the motion of the system. because really inside the system these two are canceling each other out. They don't even come into play. Okay, so they don't change the motion of the system. Maybe the best way to understand this is to do an example. So I gave you a sheet today, Newton's third law questions, and the first examples aren't going to have any friction on them, and that'll be a good thing. Okay, so the first question is, a 1,000-kilogram cart is pulling two trailers in a row. So one trailer, two trailers, car. The car is 1,000 kilograms. This is trailer number 1, and it says it has a mass of 1,500 kilograms. And this is trailer number 2, a mass of 2,000 kilograms. Okay, it says starting from rest, so VI is 0. They accelerate to 36 kilometers per hour, so VF is 36 kilometers per hour, which you need to change to meters per second. And remember, our shortcut is divide by 3.6. And so it'll be 10 meters per second. And it does this in 5 seconds. If we have a VF, a VI, and a delta T, we can find our A. A is equal to VF minus VI over delta T. So 10 meters per second minus 0 over 5 seconds. The acceleration of this this car and trailer system is 2 meters per second squared. Okay, so that's part A. Part B says, find the force the car must generate to accelerate the trailers. So when you want to do that, you want to look at the whole system, because the whole system is accelerating 2 meters per second squared, and the car is pulling them all. Okay, so we can put them all together in like one big block, and when you add up all their masses, 1,000, 2,000, so that's 345 kilograms. And we're looking for this force the car is generating thanks to its engine to pull the whole system forward. Okay, so this 45 is the 1,000 from the car, the 2,000, and the 1,500. Okay, and so we do sum of the forces in the x direction is equal to max. And I'm starting with the x direction because there's no friction, so I don't need the Fn. And if there's no friction, there's only one force in the x direction, and it's going to be equal to m total times A, because it's the total mass. So F must be equal to 4,500 kilograms times 2 meters per second squared. The force the car needs to generate to accelerate the whole system 2 meters per second squared, 9,000 newtons. Part C says, find the force of tension between the trailers. So now to find the force of tension between the trailers, you need to look at one object or the other. So, and it's always a good thing to start with the back one. So do on number 2. Why start with the back one? Because it'll have fewer forces on it. So this guy is 2,000 kilograms, and the only force it's experiencing is the force that trailer 1 is putting on it. So when you do sum of the forces on 2, it will be equal to m2a. And so the only force is F12, m2, oops, I guess I could write that down again. So F12 is equal to 2,000 kilograms times 2 meters per second squared. So F12 is equal to 4,000 kilograms. And then the last question, force between the car and trailer 1. So now we could look at trailer 1. So on number 1. And on number 1, which is 1,500 kilograms, there's the force we just found, 1, 2, pulling back, and the force of the car on 1 pulling forward. It's why we couldn't start with this one, because we wouldn't have known either of them. But now that we know the force that 1 is putting on 2, that's also the force that 2 is putting on 1. So sum of the forces on 1 will equal m1a, and so forward will be F car on 1 minus F12 is equal to m1a. You're looking for the car on 1, so m1a plus F12. So M1 1500 times